Hi, everyone. I'm Jose Juan Palacios Perez. I'm part of the UK IBM CEF team. I'm based in Manchester. Last year, I had the opportunity to give a lightning talk about my experience of testing, performance testing Crimson. So this lightning talk is intended to be a checkpoint 56 weeks later. So just a quick recap of the main ideas of the Crimson OSD architecture. On the top side of the slide, we have the traditional classic OSD architecture in which we have the several components, the messenger, the placement groups, administrator, and the object store, in which needed to be a number of threads doing the communication and passing jobs between these components, and involving synchronization primitives, involving mutual exclusion in order to have excluded access to the shared resources. On the other hand, we have the Crimson architecture, in which is supported on the SASTAR framework, which allows to provide mechanisms for asynchronous communication and asynchronous computation in general. Is based on futures, promises, and coroutines for the latest C++20 features. And instead of using several threads or a number of pooling threads, in Crimson, we have everything pinned, a single reactor per CPU core pinned, so that all the work is streamed and there is no need for explicit mutexes or sharing resources. So the potential conditions between sharing is reduced, and no need for the operating system for doing the scheduling. So these are the key points that I mentioned, the shared nothing architecture for the OSD, and in particular, an important point of the CPU core strategy that I will mention in future slides later on. So this, again, just the main highlights after 56 weeks, the progress in general as in terms of the project that he has already mentioned in the morning. So I will not mention much details. These are the highlights in terms of performance. Essentially, I showing the two representative examples in terms of the random workloads for read and for write. And it's interesting because it shows the performance of Crimson for read, 4K read, being superior of that of the classic, whereas in the random write case, Crimson still has the opportunity to improve. This is also interesting to note as a part of the experiment, when Crimson is using a single reactor per core versus 2 reactors per core. So that is a difference that is going to be interesting to notice in the messenger that I will going to take in a few slides ahead. So now in terms of my modest contributions, in reverse chronological order is the CPU core reactor pinning for all these previous experiments that I needed. There was not a tool available for me to experiment to dedicate reactors or pinned to a specific cores. So in Intel two-socket architecture, I needed to explicitly say I want these cores. I need these reactors in this particular sockets on this core or in this other. So I needed to deliberate a PR in which I proposed a CPU reactor pinning strategy, basically for OSDs balanced or NUMA socket balanced. There is the caveat is that was only intended for Intel architectures that didn't have a different hardware available at the moment. But fortunately, some produced a PR extending and improving that code, and it works for AMD architectures as well. So, and we have a detailed block, performance block in CEF for the different tests that we use and the object storage in terms of the BlueStore, CyanStore, and C-Store. This is what it looks like. So this is the command line for the vStart developer mode for getting clusters. The option here indicates the number of reactors for each OSD. And here is the algorithmic policy to allocate the reactors to the corresponding cores. This is my Python code to show in a more friendly way. I started using bitmask previously, but they were not very friendly. You can get used to after a few tries, but I think it was a much better approach. And also, if we wanted to show blue star threads, it would be necessary to show it in a different color. In this case, we're showing just a case in which we have the 3 reactors per OSDs and distributed accordingly on each of the socket, the NUMA sockets. I'm not showing performance results for that. Please refer to the blog because they are detailed and there is not a clear gain in the sense that there are some workloads that get benefit for a particular allocation strategy, but not all. The next contribution is the IOP cost estimation. Essentially, we were contacted by Kyle Bader from our community Slack, Crimson. And as a part of the discussion, we produced a plan, we produced some results comparing Crimson and Classic, and we come up with a metric to essentially just provide, according to the capabilities of the hardware, the CPU, where it's essentially a ratio of the speed of the CPU in terms of the utilization for the reactors. This refers to the reactors utilization. We could use the top metric from the CPU, but since the reactors are continually polling, it should be more clear, more precise to use the internal metrics provided from the OSD. Well, that mostly involved creating code to process, to collect and filter and present the data as pandas, data frames. There is a project for this tool, and the performance reports as a result of that. This is just the highlights. Not I'm going to show all the metrics and the description of the results, but just to give an idea of the comparison using that ratio in terms of Classic versus Crimson for Systor only, and a brief description of the machine that I was using for that. Next is the Crimson versus asynchronous messenger. This is also an interesting aspect because as part of being one of the components of the OSD, is the first one that receives the request from the client. And it was interesting to try to analyze it in an isolated way. Jing Sheng wrote a benchmark, a synthetic benchmark for the messenger a few iterations back. So I wrote code to try and test the different scenarios, modifying the CPU cores, modifying the allocation strategy, and collecting performance metrics, producing flame graphs. Something that was very interesting for that analysis is you can see some huge towers, and those are results of the lambdas in terms of the future and continuations execution of the asynchronous computation. So I needed to write some code to reduce that or transformers in a way that is more palatable or most useful for analysis. In particular, essentially, it's just a multiset associated for each of those code paths. So this is still analysis in progress, because as you are going to see in the next slide, in which we show side by side the Crimson messenger versus the Classic or asynchronous messenger, there is still space or still opportunity for making improvements. The sweet spot is around the 16 cores. I'm using each one-to-one mapping between clients and cores. So we were expecting that it was to be a continuous linear growth. This suggests that there is some resource contention that we need to continue analyzing. This is not at the scale. You can see the throughput here, the 3,000 IOPS versus 1,200. So the difference will be a bit dramatic, so I prefer to keep it that way to not give a bad impression. But yes, as I said, it's something that we continue analyzing and has a space and opportunity for improvement. As already my colleague Lee mentioned in his talk, I've been contributing to the benchmark tool, and essentially I've been producing some PRs for that. In fact, my first ever PR for Ceph was in Ceph, producing the workload section for the support of workload tests in Ceph. But I also have been producing, in particular, the automated test generator for the regression testing. Essentially, it's just serializing the classes in Python that were available at the time, producing JSON data for that, sign it with MD5 sum, so the generator will go compare for each of the attributes of the class, whether it was not being tampered with the original baseline. So the workload now is that if a developer wants to make improvements or refactoring of the CVT, it will run first the test to verify that everything is fine, then make their changes, run the generator. The generator will create unit tests for its no code changes, and then run the test again. So, and that will be part of the of his PR. So that's the intention, to support the refactoring and extension of this tool. Nearly finally, the future ideas. Essentially, like the first one is, all this could be like a wish list or one to-do list. The first one refers to the performance analysis of the coroutines in CStar. The coroutines is a different way of executing asynchronous computation that might not involve these huge towers that I shown for the messenger. One point to make is that the messenger, even though that exercises the same code as I shown for the synthetic benchmark, is not exactly the same. So it does some operations different, particularly the deletion of objects. So, but nevertheless, it's useful to have this understanding and analysis. As I said, another point is to use or extend the porting to Crimson of a project that was presented in the Cephalocon a couple of years back, in which it has the opportunity to do monitoring in real time the latencies for each of the codes segments that were interested. So, for example, you instrumented your code and make some changes, and you can appreciate almost in real time the latency that was affecting that code change. So the difference is a bit complementary to what we do with flame graphs, because once you run your test, collect your flame graphs, and proceed to the analysis, this tool will make it possible to have it pretty much real time. You do the change and you appreciate the latency. So that will be useful to attribute to each of the components the latency in which is distributed. And this doesn't refer to Crimson, but this is something that it seems quite interesting for legacy code that exists in Ceph. Finally, for me, the more important slide is the feedback that I received so far from the community for the encouragement and the environment that it makes for us to grow in all the details. So that's me. Thank you very much for your attention.